Hello and welcome. Today we are going on a journey from the physical wires you can actually trip over in a server room all the way up to the abstract, almost magical world of the cloud. We're going to peel back the network's hidden layers. So let's dive right in.
You've probably thought about this, right? It's a fantastic question. It really does seem like some kind of trick. You've got one box, one piece of hardware, but somehow it can be sliced and diced to serve completely different teams, totally securely and without slowing down. So how on earth is that even possible?
Well, the secret, it's all about a brilliant journey from the physical world into a world built entirely of software. We started by just getting smarter about managing the traffic on the actual cables. From there, we figured out how to create powerful illusions with the hardware itself. And finally, we scaled that whole concept up into the massive global data centers we use today. It's really a story of software completely redefining what a network is.
So here's how we're going to break down this journey. First up, we'll look at smarter switching, how we got clever about managing all that traffic. Then we'll jump up to the virtual layer, where the hardware gets a powerful software brain. And finally, we'll see how all of this comes together as we head into the cloud.
Okay, let's start at the most tangible level. The physical network, maybe in a dusty server closet somewhere. You see, in the early days, as networks got bigger, they just got, chaotic. They got noisy. So the very first challenge was simply to bring some order to that chaos. And the biggest problem, the worst kind of chaos, was something called a broadcast storm. This is what happens when a message that's supposed to go out to everyone gets caught in a loop. It just keeps getting forwarded and amplified over and over again. The analogy here is perfect. It's like a room where everyone starts shouting at once. The noise becomes so overwhelming that no actual communication can happen, and the entire network just grinds to a halt.
So how do you fix a problem like that? The solution was incredibly elegant. Virtual LANs, or VLANs. A VLAN uses software to slice up a single physical switch into multiple, logically separate networks. It's the perfect equivalent of putting up soundproof virtual walls in that noisy room. Now, the accounting department can shout all they want amongst themselves, but the sales department won't hear a peep, even if they're all plugged into the very same physical box. Now, we manage these virtual walls with two kinds of ports. First, you've got your access port. Think of this as the normal door into one specific room. It connects your computer or a printer to just one VLAN. But then you have the trunk port. This thing is like a main hallway connecting all the different rooms. It carries the traffic for all the different VLANs between switches while still keeping everything perfectly separated. Okay, so we've organized our traffic into these nice, neat VLANs. We're feeling good. But what about reliability? You don't want one bad cable to take down the whole network. So naturally, you add extra connections, redundant paths. But wait a second. Doesn't creating multiple paths between switches create the exact kind of loops that cause those broadcast storms we were just trying to fix? Yep, it absolutely does. We solved one problem only to walk right into another one.
And this is where our next piece of software genius comes into play. The Spanning Tree Protocol, or STP. Its entire job is to let you have that physical redundancy without the risk of creating those network-killing loops. It intelligently scans the network and logically blocks any path that isn't needed, making sure there's only one active route at any given time. And it's worth noting, a newer version called Rapid Spanning Tree, or RSTP, does the same thing, just a whole lot faster. So, how does it work? It's actually pretty simple. First, all the switches hold an election to choose one switch to be the root bridge. That becomes the center of their universe. Then, every other switch calculates the single most efficient path to get to that route. And what about all those other extra redundant links? They're put into a blocking state. They just sit there, ready and waiting to jump into action the second that primary path fails. It's a built-in safety net. All right, so we've brought order to our physical network. Now, let's move up a layer in our journey of abstraction. We're moving from just managing traffic to something much cooler, creating illusions with the hardware itself. Think about it. We've brought all this logical order to the network paths, but the servers themselves are still just, single physical machines. What if we could take that same idea of logical separation, those virtual walls we used for traffic, and apply it to the computers themselves? What if one server could safely and securely pretend to be 10 different servers? And that, right there, is the core idea of virtualization. It is the art of creating a logical version of something that isn't physically there. We use software to take one seriously powerful physical server and carve it up into multiple, totally isolated virtual machines, or VMs. Each one of these VMs gets its own little slice of the physical resources and acts like it's a completely independent computer. The magic behind all of this is a piece of software called a hypervisor. And honestly, the best way to think about a hypervisor is as the apartment manager for your server. If the physical server is the entire apartment building, the hypervisor's job is to create all the individual apartments, those are your VMs, and then make sure each one gets its fair share of utilities like CPU power, memory, and storage. And this apartment manager comes in two main flavors. You've got your Type 1 or bare metal hypervisor. This is the foundation of the building itself. It's installed directly on the hardware. This is what you find in big data centers where you need maximum performance. Then there's the Type 2 or hosted hypervisor. This one runs like any other app on top of your normal operating system, like Windows or Mac OS. It's like building a new apartment inside a house you already live in. It's awesome for testing and development right on your own laptop. Okay, so if a VM is a virtual computer, how does it talk to the network? Well, it gets a virtual network card, or a vNIC. The hypervisor creates this little piece of software for each VM, giving it a unique identity and its own connection to the virtual world. And to connect all these vNICs together, we need a virtual switch, or a vSwitch. This is literally a software-based switch that lives entirely inside the hypervisor. It's the traffic cop that directs data between all the different VMs running on the same machine, and it also handles connecting them to the physical network outside. It uses different modes like bridged or NAT to control how that happens. It is literally a network in a box. And this brings us to the ultimate step in this virtual layer. Network Functions Virtualization, or NFV. This is where we look around and say, hey, why stop with servers? Let's turn everything into software. So instead of buying an expensive, specialized piece of hardware to be your firewall or your router, you can just run it as another virtual machine on a standard off-the-shelf server. This has been an absolute game changer, especially for big telecom companies, letting them build and scale their networks with unbelievable flexibility. All right, time for our final section. We're going to take all these amazing concepts, virtualization, NFV, and scale them up to a degree that is just mind-boggling. We are heading into the cloud, which, when you boil it down, is really just someone else's giant virtualized data center that we can rent a piece of. You could say cloud computing is just virtualization as a service. But what makes it truly revolutionary are its core characteristics. Things like on-demand self-service, broad network access from anywhere, and massive pools of shared resources. Instead of buying and managing your own hardware, you just access these vast, scalable resources right over the internet. And there are really three main ways to deploy it. You've got the public cloud, think Amazon Web Services or Microsoft Azure, where the provider manages everything and you share the resources with other customers. Then there's the private cloud, which is built exclusively for one organization, giving them total control. And of course, the hybrid cloud, which mixes and matches, giving you the best of both worlds. Across these, you can get anything from raw servers, that's infrastructure as a service, all the way up to ready-made apps, which is software as a service. So there you have it. That's the whole journey. We started with a very real, very concrete problem, tangled up traffic on physical wires. We solved that with clever software logic, like VLANs and STP. That, in turn, opened the door to virtualizing the hardware itself with hypervisors and VMs. And that foundation is what enabled the massive on-demand infrastructure we now just call the cloud. It's really an incredible progression, isn't it? From concrete to pure abstraction. The physical network, the cables, the switches, it's all still there, of course, but it's now almost entirely managed and defined by software. This shift has unlocked possibilities we couldn't have dreamed of just a few years ago. So the final question we have to ask ourselves is, now that our networks are becoming nothing more than lines of code, what will we build next?